This is part D of question number 2-4 from Corman. Give an algorithm that determines the number of inversions in any permutation on n elements in theta of n log n worst case time. And the hint given is that we need to modify the merge sort algorithm to compute this number. Now we can assume for this problem that this permutation on n elements is given to us in an array. So let's call the array as A, and it has indices from 1 to n, and the order of elements in the array is that permutation. So in other words, you're given an array of n numbers and you want to compute the number of inversions in it, and you want to compute that number in theta of n log n time by modifying the merge sort algorithm that we've seen so far. Now before we look at the specifics of computing the total number of inversions, we need to recap the essential features of merge sort, because we are asked to use that algorithm to compute the number of inversions. So merge sort takes the larger problem and divides it into two subproblems. So this original problem, which is the problem of sorting an array of size n, is divided into two subproblems. So the array A is going to be divided into a left half and a right half, and merge sort is going to be recursively called on those subproblems. So the left half will be copied into a separate array and merge sort will be called on that array. The right half will be copied into a different array and merge sort will be called on that array. And after these recursive calls return their result, the result will be the sorted versions of these arrays. Then these sorted arrays are combined by the merge step of merge sort into a larger sorted array. So this is the sorted version of A. And we've seen how merge sort works in a previous video. Now, what this question asks you to do is to compute the number of inversions alongside. So as you are going through the merge sort algorithm, as you are executing the merge sort algorithm, is it possible to tweak the code so that you can compute side by side the number of inversions in A. Now, since merge sort is a recursive procedure, we can assume that when we recursively call merge sort on the left subproblem and the right subproblem, we are also going to get, as part of the result of the recursive call, the number of inversions in the left subarray and the number of inversions in the right subarray. So that information is going to automatically be provided to us by the recursive call. So using those two numbers, the number of inversions in the left subproblem and in the right subproblem, or in the left subarray and in the right subarray, can we calculate the number of inversions in the original array? If you think about it, the number of inversions in the original array are going to be equal to the number of inversions within the left subarray plus the number of inversions within the right subarray plus what I call as the number of cross inversions. So putting it in a different way, let's say this is the original array A. We know that an inversion is a pair of elements from A where the left element has a lower index than the right element, of course, because it is the left element. Elements to the left have a lower index, and the value of the left element is more than the value of the right element. So I can, let me use my own terminology here. Let me call this as the left leg of the inversion. Let me call the left element of an inversion as the left leg and the right element as the right leg. Now, an inversion within the left subarray is one where both the legs of the inversion lie within the left subarray. An inversion within the right subarray is one where both the legs of the inversion lie within the right subarray. So both the elements that we are talking about fall into regions within the right subarray. So this is an example of an inversion in the right subarray. This is an example of an inversion within the left subarray. This is the halfway mark here. A cross inversion is one where the left element comes from the left subproblem or the left subarray and the right element comes from the right subarray. So the inversion is crossing the boundary of the midpoint. So the left element is in the left side and the right element is on the right side. Now the first two values, number of inversions within the left subarray and the number of inversions within the right subarray, both these values are provided to us by our recursive call to this on the subproblems. So alongside sorting the array, we're also computing the number of inversions in the array. So when we invoke merge sort or this modified version of merge sort on the two smaller subproblems, we are going to get sorted versions of those two subproblems, and we are also going to get the number of inversions within those two subproblems or subarrays. But we still need to compute the number of cross inversions if we want to compute the number of inversions within the original array. So how do you compute the number of cross inversions? To compute the number of cross inversions, we need the following information. And this follows from the definition of what an inversion is. For every element in the left subarray, we want to know how many elements in the right subarray are smaller than that element. Okay, so if for every element in the left subarray, let's say I take this particular element, how many elements in the right subarray are smaller than this element? Because if there are 5 elements here that are smaller than this element, I know that there will be 5 inversions created by this element. When I combine this element with each of those 5 elements, I'm going to get 5 inversions. So we need to compute the number of elements in the right subarray that are smaller in value than the given element of the left subarray. And if we add up this number over all the elements of the left subarray, we will get the total number of cross inversions. I'll come to this point later. But let's try to see how we can compute the number of elements in the right subarray that are smaller in value than a given element of the left subarray. When we are merging the two sorted subarrays in the merge step, what we're going to do is we're going to track at each step of the merge procedure. We're going to keep track of the number of elements from the right subarray that have already been added to the merged array so far. Okay, so for example, let's say this is the left subproblem, this is the right subproblem. sorry, this is the left sorted array, this is the right sorted array. And in the merge step, we are merging together these two lists to form a larger merged array. So we're going to have pointers pointing to the heads of both the lists, and then these pointers are going to be incremented, and elements from both these lists are going to be appended to this answer list, to this merged array in increasing order. So what we're going to do is we're going to track the number of, at every step we're going to track how many elements from this right subarray have been appended into the answer list. As the merge procedure goes forward, we are going to continuously keep track of that value. So whenever we append an element from the right subarray to the merged array, we are going to increment that counter. So think of a counter maintaining the count of the number of elements in the right subarray which have been added to the merged array. Of course, at the end of this merge step, the counter value is going to be equal to the length of this list, because at the end every element from this list would have gotten added to the merged array. And at the very beginning, the counter value is going to be 0. And whenever we add an element from here to the merged array, we're going to increment the value of the counter by 1. So let's assume that this counter is nothing but a variable, an integer variable called count so far, which is counting the number of elements from the from this list which have been added to the merged array so far, and this counter is keeping track of that count at every step of the merge procedure. Now, when an element from the left sub array, so let me call this let's take an arbitrary element. Let me call that element as x. So let's say that at some point of the merge procedure, we decide that x is going to be added to this answer list. So clearly, all the elements before x would have already been inserted into the merged array at some point before we come to examine x. And likewise, all the elements here that are less than x would have been inserted into the merged array, because it's only after all those elements less than x are inserted that we will decide to insert x. Right? If there is any element here, so if the pointer into this list is pointing to an element that is larger than x, only then will we decide to insert x. If the pointer is pointing to an element whose value is smaller than x, then why would we insert x at that point? We'll first insert this element. So at the exact point of time where we decide to insert x into the merged array, the elements that are less than x in this array have been already added to the list. And we know how many elements have been added. That's the value of this counter. So when an element from the left subarray, say x, is added to the merged array, this counter called count so far is going to tell you how many elements in the right subarray were smaller than x. Because they were smaller than x, that is why they were added to the merged array before x. So if we know this counter value, we know the number of cross inversions where the left leg is x, or the left element is x. Because x, when paired with each of the elements that the counter has counted, is going to create an inversion. So if we sum together this number which we computed for x over all such x's in the left subarray, if we compute this number for every element of the left subarray, so whenever we are appending an element from the left subarray into the merged array, we're going to compute what that value is, and that value is going to be this counter value count so far. And then we're going to keep adding So that's the number of cross inversions involving that particular element as the left leg. And we're going to keep adding that value for every element in the left subarray. And once we do that, we will get the total number of cross inversions. Okay. So the total number of cross inversions is summation over all x, the number of cross inversions with x as the left element. And this value, the number of cross inversions with x as the left element, is the value of this counter count so far at the time when x is added to the merged array. And we're going to do that for every element in the left subproblem. Okay, so for all x in the left subproblem, for all x in the left subproblem, we sum together the number of cross inversions where x is the left element. And that's the counter value at the time when x is being inserted. So this summation is going to be the total number of cross inversions. And if we know the total number of cross inversions, we can compute at that stage the total number of inversions in the original array. Because the total number of inversions in the original array is the sum of these three numbers, two of which we already know based on the recursive calls, the results returned by the recursive calls. And the third number is what we calculate alongside the merge step of merge sort. So by adding together some, this code for keeping track of these counters and summing up the values of the counters at different points, the merge step of merge sort can be augmented to return this information, the number of cross inversions. And once we know this information, we can compute the number of inversions within the original array. Now, one small point here needs to be clarified, that uh, in the base case where merge sort is invoked on an array of size 1, the base case of merge sort is going to return uh, that singleton element or that array of length 1 without doing anything. But because we also want every call to merge sort to return the number of inversions in that array, we need to specify what the base case is for the number of inversions when merge sort is called on an array of length 1. And the number of inversions in an array of length 1 obviously is 0. So having specified the base case and having specified how the recursive calls to the two subproblems are going to be combined, we can compute the number of inversions in the original array via this modification to merge sort.